Hello, this is Mr. P, and today we're going to learn more about graphing the trigonometric functions. In the last section, we covered sine and cosine. In this lecture, we're going to cover tangent plus the three reciprocal functions, which would be cotangent, secant, and cosecant. All right, but first, let's do a little bit of a review of what we learned last time, which is graphing sine and cosine. So here's a problem to get you back into the swing of it. If you want, go ahead and pause the video now and graph this, and then come back and we will see how you did. Okay, hopefully you've graphed it by now. So if we look at the four pieces of information that we want to find with all of these graphings, we want to first look at the amplitude, and that's going to be the absolute value of the coefficient of the trig function. So absolute value of -2 is a +2. That will be our amplitude. That's the distance from the center to the top, or the distance from the center to the bottom. For the period, we want to look at the coefficient of x inside the argument, and our period is 2 pi divided by that coefficient. So 2 pi divided by 2 is simply going to be pi. Phase shift is another way to ask for the left endpoint. Left endpoint and phase shift are talking about the same point. And for that, we want the value of x that causes the argument to be 0. And in this case, if you do the algebra, that would be pi over 4. Simply take the expression set equal to 0, add pi over 2 to both sides, and divide by 2. And you're going to get pi over 4. For the right endpoint, you can find the value of x that causes the argument to be 2 pi. Or you can take the idea that the left endpoint plus the period is going to equal the right endpoint. And no matter which way you do it, you're going to get 5 pi over 4. One other thing you should be aware of is the negative sign outside means that there's going to be a reflection. And since we're outside of the parent function, that is going to be vertical. So there is a vertical reflection. You should note that in your side work. All right, now we should be ready to go ahead and graph this. Since our amplitude is 2 and there's no shifts up or down, our vertical scale, we want to make sure we can fit in +2 and -2. And if we go horizontally, I do notice that these points are pi over 4 or 5 pi over 4, so we have that over 4 fraction. So that's the scale I'm going to choose horizontally. So I want 1/4, 2/4, 3/4, and then 4/4 would be pi. That's the scale I want horizontally. That'll make it easiest to graph. All right, now we're ready to start with the left endpoint, which is pi over 4. So at pi over 4, the cosine curve normally starts out at a maximum. However, since we are reflecting vertically, it's actually going to start at the minimum. And the amplitude of 2 tells us the distance from the center to the minimum is going to be 2. So that will be our first point. If you know your left endpoint, then you also know your right endpoint because they will be at the same value. So at 5 pi over 4, it's always going to end up at the same point. That way the pattern can repeat. So halfway between two minimums will be a maximum. So at this point here, you're going to have a maximum, which will be a +2. And then halfway between a minimum and maximum will be an intercept. Halfway between these two extrema will be another intercept. And so those are the 5 key points that we want to graph. Now also notice the directions did say to graph only one cycle of the graph. So if we draw a smooth curve through them, we don't actually have the arrows on this graph because they did ask for just one cycle. So we do have true endpoints on the left and the right. And that would be the graph of this equation. All right, so now we're going to go ahead and look at the graphs of tangent and cotangent, secant, and cosecant. So we're going to start out with a little bit of a background, though, of positives and negatives. If we look at the 4 quadrants here, we have our unit circle, which has a radius of 1. And if we have our initial side as the positive x-axis, we're going to open up an angle, and we're going to call that angle theta. And then it'll open up to some terminal side. So the point on the unit circle, that will be called the terminal point. And if we drop a perpendicular from that point, then we create this nice little reference triangle. Now, in the unit circle, the important thing to understand are definitions of sine and cosine is that the sine is the length of this segment that is opposite the angle. So the length of the segment is the geometric definition of sine. And the length of this segment, the blue one, is the geometric definition of cosine. So the important thing to realize here is that the point, the terminal point, has the coordinates cosine, sine. So if we look at the coordinates of this terminal point, it would be cosine comma sine. So therefore, cosines are x values and sines are y values. So with that, we can figure out what quadrant sine is positive or negative and cosine is positive or negative. In quadrant 1, everything's positive. So you know both sine and cosine are positive because your x's and your y's are positive. In quadrant 2, we have a negative x and a positive y. That means we have a negative cosine and a positive sine. Quadrant 3, both of them would be negative because negative x, negative y, so they're both negative in quadrant 3. And in quadrant 4, you have a positive x, negative y, which translates to a positive cosine, a negative sine. Those signs are going to be important to remember when we start to create the graphs. All right, so looking ahead, we're going to now look at the tangent curve. So we're going to find the graph of the tangent, y equals tangent of x. One more important thing to realize with that last diagram was that the input of the sine and cosine functions is an angle, and the output is the length of a segment. That'll become important later when we do inverse trig functions. But for now, we're graphing tangent, so y equals tangent of x, and the way we're going to analyze this is we're going to think of tangent of x as sine divided by cosine. That's why I'm showing for reference, this is our sine curve, this is our cosine curve. We see how they work together to create the tangent curve. So starting out with the fraction here, we're going to treat this as we would graphing a rational function. We're going to look for the zeros of the numerator, we're going to look for the zeros of the denominator, and we're going to start with the denominator because whenever your denominator is 0, that you have division by 0, which is not allowed, so that will create an asymptote. So we think of the cosine of x, wherever cosine, which is this curve, wherever cosine is 0, you will have an asymptote, and it will be a vertical asymptote. So if we look here, we have pi over 2, 3 pi over 2, 5 pi over 2, and even the negatives, negative pi over 2, negative 3 pi over 2. So for every odd multiple of pi over 2, we will have cosine equals 0, so tangent will have a vertical asymptote. So that'll happen looking at our scale. I've already put the scale on there, but we can look at negative pi over 2, there's going to be a vertical asymptote, at pi over 2, and then 3 pi over 2, 5 pi over 2, etc. That pattern will repeat indefinitely, and you will have an asymptote at every odd multiple of pi over 2. Now for the zeros of the numerator, that is where you are going to get your intercepts. So whenever the sine is 0, that will cause a point to be on the x-axis. So looking at the sine curve, sine is 0 at 0, but also at pi or 2 pi, or if we keep going 3 pi and negative 2 pi, etc. So every multiple of pi has a value of 0 for the sine. So if we look at 0, we know that point, that intercept, that point is going to be on our tangent curve. And likewise, it's going to be at pi, it's going to be at 2 pi, it's going to be at 3 pi, etc. So for every multiple of pi, you will have an intercept. Now, if we concentrate on this section, this represents quadrant 1 on the graph, because we're going from 0 to pi over 2, which is quadrant 1 for our angles. So here, if we think about the way we analyze the rational functions, as we approach from this point, as we approach the asymptote, I'm either going to approach it going in this direction, or I'm going to approach it going in this direction. All I really need to know is, am I going to be above the line or below the x-axis? Well, you can sort of figure that out with the positive or negatives that we looked at in the last one. Since you have sine divided by cosine, we know in quadrant 1, sine and cosine are both positive, so it's definitely going to be positive. So the graph will go upwards in this quadrant. And in 0 to negative pi over 2, which is quadrant 4, well, in quadrant 4, we have a positive cosine and a negative sine. So a negative over a positive is going to be a negative. And that will be how the graph goes in quadrant 4. Now, usually this is good enough for your graphs. You don't really need to put other points, but there is one point I want you to be aware of, although you don't have to put it on your graphs. I do want you to be aware that for scale-wise, if you have halfway between the 0 and your asymptote, which would be pi over 4 is halfway between 0 and pi over 2, that the tangent of pi over 4, remember pi over 4 is a 45-degree angle, so that would be a 45, 45, 90 triangle, and your tangent is going to be 1. So if you needed extra points to plot, then you know that at pi over 4, the value of tangent is 1. And that's an important point to know for your transformations. Let's say we wanted to graph 3 tangent of x. Then multiplying outside will stretch this vertically. So instead of that point being at pi over 4, comma 1, it's going to be pi over 4, comma 3. So this point would just move up to 3, and yet the intercepts would not change because they're on the axis, and the asymptotes would not change with vertical stretching. So this is the point that's actually going to change if you have a number out front. So keep that in mind, although when you're actually graphing the tangent, usually don't plot that point. Now if we look at the next region between the two asymptotes, we have quadrant 3 and quadrant 4. This would be quadrant 2 and quadrant 3. For quadrant 2, we're going to have a negative, if we think of our x and y's, we're going to have a negative x and a positive y. So that would be a positive over a negative, which is going to be a negative. And in quadrant 3, we have both of them being negative, so a negative over negative is positive. Or you can even look at the graphs for that. In quadrant 3 would be between pi and 3 pi over 2, so you see sine is negative and cosine is negative. So negative over negative is a positive. And this is an interesting change in that the period of this function is actually pi and not 2 pi like sine and cosine. It's a coincidence of a positive over positive or a negative over a negative both being positive. And here it doesn't matter whether it's negative over positive or positive over negative, you're still going to get a negative. Because of that, the symmetry created here means that this shape actually repeats itself every pi. So once I know that, then the other sections are all going to be exactly the same, and we create that same curve. So it goes on forever to the right and to the left. So it is important to remember properties, though, that the period of the tangent curve is actually pi and not 2 pi, like sine and cosine is. All right, so that is our tangent curve. Let's take a look at our cotangent. And we're going to approach that the exact same way. Still, cotangent is made up of cosine and sine. Matter of fact, it is cosine divided by sine. So we're going to start with the same grid here, and the same analysis. We first look for asymptotes. Where does sine equal 0? Well, sine equals 0 at 0, pi, 2 pi, etc. So we know we have an asymptote is going to be the y-axis. Now, when the y-axis is an asymptote, you don't really need to draw dotted lines or dashed lines. You can just leave it as the y-axis. Just keep in mind that it is an asymptote. But then we're also going to have pi is going to be an asymptote, and then also 2 pi, 3 pi, etc. Every multiple of pi will have an asymptote. And the zeros of the numerator, those are going to be our intercepts. So the cosine, wherever that is 0, which is at pi over 2, 3 pi over 2, 5 pi over 2, those are going to be our zeros. So at the points in between the intervals, right in the center of them, is going to be our intercepts. And now the same analysis, if we look at this block here, which is quadrants 1 and 2. In quadrant 1, everything's positive, so we're either going to go up or we're going to go down, but since everything's positive, we know we will be going up. And in quadrant 2, we have one positive, one negative, so we're going to be going down because a positive divided by negative divided by a positive is going to be negative. And if you want that additional reference angle, notice that it will go through pi over 4 comma 1. But from here on, we know that for the same reasons as tangent, this represents the complete cycle of the graph. So this shape is just repeated in each of the other intervals between the asymptotes. And even on the left here, it does continue to the left. So using that same analysis, we can create this graph. And then a quick little recap of all the properties here. We can see that for the tangent curve, our period is pi. Just like with cotangent, our period is pi. The domain for tangent will be all real numbers except where you have your asymptotes. And you have your asymptotes. This would be how we express it as an interval, and the idea is that it's every odd multiple of pi over 2. The range, which are y values, notice how it goes up forever and down forever, so the range is all real numbers. And notice how the vertical asymptotes is where the graph is not allowed to be. For cotangent, your range is going to be everywhere except where we have the vertical asymptotes, and the vertical asymptotes occur at multiples of pi. And of course, the same range for cosine as well, all real numbers. Alright, so that's tangent and cotangent. Now we want to look at secant and cosecant. We're going to start with the secant curve. And the way we're going to derive this is we're going to realize that the reciprocal of secant is cosine. So secant is 1 over cosine. So we need to know about the cosine curve, which we have here. And there is going to be an asymptote because there are values that cause cosine to be 0. So wherever cosine is 0, which again is odd multiples of pi over 2, those are going to be asymptotes. So at 1 pi over 2, 3 pi over 2, 5 pi over 2, etc., those are going to be vertical asymptotes because you can't have division by 0. Now, unlike the other curves, there is no value of x that would cause the numerator to be 0. Notice how the numerator is a constant. It will always be 1. So this graph, that means this graph will never touch the x-axis. That's an important thing to realize. There are no x-intercepts. So how do we analyze this? Well, we're going to look at the halfway point, which represents the maximums and the minimums for the cosine curve. We see when it's 0, we have an asymptote, and between two zeros, you have either a maximum or a minimum. So starting with pi, let's see what happens at pi. At pi, we have a minimum, which is going to be -1. So at pi, we have -1, which would be that point on the curve. And if we looked at what happened at 0 we have a maximum, which is a +1. And by the way, I am substituting that into this expression. So 1 divided by a +1 is a +1. 1 divided by a -1 is a -1. So I have those 2 points. And then notice when I get to 2 pi, I have the same thing I had at 0. So I'm going to go positive, negative, positive, negative, and finally positive. So positive, negative, positive, negative, positive. Now within the interval, and by the way, we do also have an asymptote here at negative pi over 2. So within this interval, this is our first interval we're going to look at. From this point, as I approach to the right or I approach to the left, I'm either going to approach the asymptote this way or I'm going to approach the asymptote this way. But if you remember earlier, we said since the numerator can never be 0, there's no way that this graph is going to touch the x-axis. So right off the bat, without even having to plug anything in, we know this is going to go upward as we approach the asymptote. Likewise, as we go to the left, it's going to go upward because we can't touch the x-axis. Same thing as if you look at this interval. I'm either going to go towards the asymptote this way or towards the asymptote that way. But again, I'm not going to touch the x-axis, so I know it must go down on both sides, which gives us that curve. Now it's worth noting though that although these look like parabolas, they are not parabolas. These curves are not parabolic in shape. They are trigonometric. Remember that a parabola goes up and to the right forever. It doesn't have an asymptote, where these just get closer and closer to the line but never touch the line. All right, so this pattern, as we get to the next cycle of the cosine, will repeat. So this curve will do the same thing here. This curve will do the same thing here. And these branches just give that repeating pattern. So this is the graph of secant. And there is another way we can think of it. Some people like to think about and actually plot lightly plot the graph of cosine itself. And if we do that, we're going to see something interesting. This is the graph of the cosine curve. And notice how wherever you have the cosine curve hitting the axis, that will cause an asymptote. And wherever you have a maximum or a minimum, that'll be a point on the secant graph. And then the branches go away from either the maximum or the minimum. So some people like to actually graph these by lightly creating the cosine curve, and then from the maximums go up on both sides, or down on both sides. Don't forget to draw your asymptotes as well. And then after you've created that graph, you would actually then erase the cosine curve. Because remember, the cosine curve is not part of the secant curve, but you can use it to create it. And that's actually the method we're going to do for cosecant. You can see that we can make it a lot faster if we do it that way. So let's look at the cosecant graph. And again, the idea here is the fact that cosecant is the reciprocal of sine. So we're thinking about our sine curve, and as a matter of fact, we're going to go ahead and plot that sine curve. So we're going to lightly plot the sine curve. Wherever sine touches the x-axis will cause division by 0, so that will be an asymptote. So the y-axis here is an asymptote. Also here, we're going to have an asymptote. So here we're going to have an asymptote at pi, 2 pi, 3 pi, and also 4 pi, etc. Those are all going to be asymptotes. And then wherever we have a maximum, there's going to be a point that's on the cosecant curve. Likewise, wherever we have a minimum, there's going to be a point. So at the minimum, maximum, minimum, maximum, all these points are going to be on the cosecant curve. And then from there, we simply are going to go approaching the asymptotes, but away from the axis. So here we're going to go up to the right and to the left of that point. Here we're going to go down to the right and left of that point. So here we're going to go down both ways. Here we're going to go up both ways, down both ways, etc. And then after we've graphed those branches, these are called branches, by the way. After we've graphed those branches, then we are going to go back and erase that sine curve. And then this is the graph of cosecant. All right, so putting together secant and cosecant, we're going to take a quick look at the properties. And our properties here. Now notice how they left the generating curve up there. They left the sine curve and cosine curve up there, but they did make it a different shade of gray, which means it's not really part of the graph. So don't get that confused. But here we can see that the period for both cosecant and secant is 2 pi, just the same as it was for sine and cosine. The domain is going to be all real numbers except the asymptotes. For cosecant, your asymptotes occur at the multiples of pi, and for secant, your asymptotes occur at odd multiples of pi over 2. So 1 pi over 2, 3 pi over 2, etc. The range, remember, neither of these two graphs will ever touch the x-axis. So there is a range, there is a y value that you will never have. For both of them, they are the same. The graphs exist at 1 or above, or at -1 and below. And in interval notation, we would say from -1 to 1, including the endpoint, unioned with 1 to infinity, again, including the endpoint. And just like the sine and cosine curves, the cosecant and secant do have symmetry. This one has origin symmetry, which makes it an odd function. And the secant curve has y-axis symmetry, which makes it an even function. Okay, those are our properties, and we're done.